Hello everyone, in this presentation I'll talk about our recent work on Meta-OLE, meta-learned orthogonal low-rank embedding. In standard feature learning trained with standard cross-entropy, the feature space, where the linear boundaries are learned in the feature space for same classes, the lack of enforcing intra-class similarity and inter-class separation leaves little space for novel classes, denoted purple and yellow dots here, to be well represented in the feature space without interference. And in the proposed method, the feature space trained with orthogonal low-rank embedding encourage feature across different classes to collapse to an orthogonal subspace, each of which has minimal dimensions. This intra-class similarity and inter-class separation allows novel class to be represented in the feature space with significant reduced interference. Specifically, this is achieved by orthogonal low-rank embedding, which is originally proposed to learn a linear transformation to recover the orthogonal low-dimensional intrinsic structure in the data, and is further extended to deep learning, where the phi here can represent any deep feature extraction. And in the first term of this orthogonal low-rank embedding, encourages the transformed representation with each of the k classes to reside in a low-rank subspace, where star here denotes the nuclear node. And the second term promotes the orthogonality of the subspace across different classes. So in our pipeline here, we can use any feature extraction here to first extract the feature of the support and also the query set of each image, given a few shot classification. Given each few shot classification task, we then optimize an adaptive orthogonal low-rank transformation for each task, which is formed as a lightweight MLP, which can be efficiently optimized without touching all the parameters in the feature extraction. And this part can be applied to each class very efficiently at a low cost. Specifically, this is achieved by gradient-based adaptation to the parameter in the adaptive orthogonal low-rank transformation, driven by the orthogonal low-rank embedding loss, given the support set features. The imposed geometry-regularization of the orthogonal low-rank subspace naturally leads to a subspace projection-based classifier that fully utilizes the obtained feature geometry. Since now the desirable feature of each class reside in a low-rank subspace, the inference of the class label of a query sample can then be effectively computed by projecting the feature vector to each subspace of classes and observing the norm of the projected vectors. In each iteration, when adapting the parameter in the adaptive transformation, we can augment the data by assigning the pseudo-label to each query sample. This can be effectively implemented by projecting each query sample to each subspace inferred from the support set, and finding the label maximum probability, as we presented before. And this achieved the transductive learning in the feature classification, without introducing any auxiliary component to assign the pseudo-label. And the proposed method achieved good performance on both standard feature classification and cross-domain feature classification, with the transductive learning setting with the pseudo-labeling further improved the results. By visualizing the feature space across the iterative updating steps, it clearly showed that the feature of each class progressively collapsed to a rank 1 subspace, and subspace of different class tend to become orthogonal to each other.